This is the notes for BSc student in physics, pressure of radiation, in which we have two parts. That is, one is normal incidence and another is pressure of diffuse radiation. First of all, we have to see the normal incidence. This is the derivation of the normal incidence. And this is the pressure of diffuse radiation. It's the derivation. It is still continuing in the next page also. The pressure of diffuse radiation here we get is 1 by 3 into total energy density. This is the pressure of diffuse radiation which we get from this derivation. Is from here we get the pressure of diffuse radiation is 1 by 3 into total energy density, and from the normal incidence from the first case we get pressure of diffuse radiation is equal to U. That means the pressure of radiation is equal to the energy density. Here U means energy density. Here P is equal to U. Here we can easily derive it by just the number of photons corresponding to the mass m is given by the theory of relativity, that is mc square is equal to h nu. So from here we can get m is equal to h nu divided by c square. Thus the momentum of the photon is equal to mass into velocity, where it is the mass h nu divided by c square. H nu divided by c square into velocity. Velocity of the photon is c, is equal to, from here we get h nu divided by c. H nu is equal to E divided by c. E is equal to h nu. For that here we have write E divided by c. E being the energy of photon. Here E being the energy of the photon. Now the momentum incident on the surface PQ per unit area per second is given by PQ. Here is the PQ surface. Momentum of incident photon which falls on the surface PQ. It is equal to P is equal to summation. Summation means it is taking all over integration, that is E divided by C is equal to summation of E divided by C. But summation E is equal to total energy incident on the surface per unit area per second, which is equal to E, say. So here substituting in equation 1, this is equation 1. Substituting in equation 1 we get P is equal to, where summation E is equal to E, so we can write P is equal to E divided by C. If U is the energy density, that is energy per unit volume, then total energy passing through area S of the surface normal to the incident radiation per unit second is equal to UC into S, where U is the energy density and C is the velocity of the light and S is the surface area. Therefore, the energy flux, that is energy radiation per unit area per second, is equal to E is equal to UCS divided by S. S means the surface area is equal to UC. So this is equation number 2. This is equation number 2. So substituting in equation 2, putting the value of E in equation number 2, which means get P is equal to UC divided by C is equal to U. If all this momentum is absorbed, it will give rate of change of momentum per unit area, that is the pressure of radiation. Pressure of radiation is denoted by P is equal to U. From here we get P is equal to U. Thus, for normal incidence on the surface, the pressure of radiation is equal to the energy density. Now, the second part, the pressure of diffuse radiation. Pressure of diffuse radiation, here this is a diagram. Diffuse radiation. Diffuse radiation means what? The photon moves in all possible direction is called diffuse radiation. The energy incident on the surface KL. The energy incident on the surface KL per unit area per second is equal to U into C. U means energy density and C is the velocity of light. If S is the surface area of the plane KL, then the energy incident on the surface KL in second is equal to UC into S. This is the surface area, but the surface area of the plane KL is equal to surface area of the plane LM into cos theta. LM into cos theta, where S dash LM into cos theta. LM, this is, if this is S, then this is S dash. So LM into cos theta, so S dash ML is equal to S dash. So S dash into cos theta here, where S dash is the surface area of the plane LM. Therefore, energy incident on the surface KL per second is equal to UC into S dash into cos theta. Therefore, energy incident on the plane LM per second is equal to UC into S dash into cos theta. Energy incident on per unit area of the plane LM per second is equal to UC into S dash into cos theta divided by surface area of the plane LM. UC into S dash into cos theta divided by S dash is equal to, where surface area of the plane LM plane is S dash. So here we can cut S dash, so we get UC into cos theta. Therefore, the momentum incident on the surface LM per unit area per second is UC into cos theta divided by C, so we get U into cos theta. Now, we will consider a hemisphere. Not now, but later on. The component of this momentum in a direction normal to the surface LM is U into cos theta is equal to U into cos square theta. If all this momentum is absorbed, then equation 5 gives the total rate of change of momentum per unit area normal to LM, that is the pressure of radiation on the surface LM is given by U into cos square theta. This is equation 5 and this is equation 6. In the case of diffuse radiation, the radiation is incident from all possible direction with equal probability. Therefore, if there are n beam of radiation meeting the surface, the total radiation pressure on the surface is given by summation U into cos square theta. now from the surface of the hemisphere. From the surface of the hemisphere, cut out of a ring-shaped element ABCD. This is ABCD by means of two cones. There is the two cones. This is the one cone and this is the another cone. ABCD. Semi-angle theta. This is the semi-angle theta. This one, and this is theta plus d theta. This is theta plus d theta. Drawn from O as apex and OY, which is perpendicular to LM, as axis. The area of the ring is given by 2 pi into sine theta into r into d theta. So 2 pi into r square into sine theta into d theta. As n beams are considered to be uniformly distributed over the surface of the hemisphere, which is equal to 1 by 2 into 4 pi r square is equal to 2 pi into r square, the number of beam crossing through the area of the ring is equal to dn, is equal to 2 pi r square into sine theta into d theta into n divided by 2 pi into r square is equal to n into sine theta into d theta. The fraction of beam incident between angle theta and theta plus d theta is equal to dn. If we take the if we take this n on the denominator of dn, we get dn divided by n is equal to sine theta. This one, n from here 2 pi into r square, 2 pi into r square. From the denominator and numerator, if we cut this, we will get n into sine theta into d theta. So from here dn divided by n, dn, here comes n, we get sine theta into d theta. The pressure P can be written as P is equal to dn divided by n into u into cos square theta into cos square theta is equal to sine theta into d theta into u into cos square theta into d theta. Here, from where we get u into cos square theta is from equation number 5. From equation number 5, this is u into cos square theta. Multiplying this on here, we get, that is dn divided by n into u into cos square theta, and the value of dn divided by n is equal to sine theta into d theta. So we get sine theta into d theta into u into cos square theta, so which is equal to P is equal to u into cos square theta into sine theta into d theta. Now if we take integration from the limit 0 to pi by 2, we get P is equal to integration from 0 to pi by 2 u into cos square theta into sine theta into d theta. Here u integration 0 to pi by 2 cos square theta into sine theta into d theta. If we substitute, cos theta is equal to x. So by differentiating, we get minus cos theta differentiate is minus sine theta into d theta is equal to dx. So we will put this value into this equation. So we get, therefore P is equal to u. Integration limit also changes, that is 1 to 0 x square cos square theta is equal to x. So cos square theta, so you will get x square into sine theta we get minus dx is equal to minus u into integration limit from 0 to 1. Here the integration limit was 1 to 0. So to remove this minus 1, to remove this u minus u into integration limit from 0 to 1 into x square into dx, we get here u into x cube divided by 3, limit from 0 to 1, P is equal to u by 3. Therefore, pressure of diffuse radiation is equal to 1 by 3 into total energy density.